In this video, we will start with the basics of Poisson distribution. Now, what is Poisson distribution? In order to understand Poisson distribution, let's talk about discrete probability distribution that we have studied before. We have studied binomial probability distribution, and we have also studied geometric probability distribution. Now, why are they called discrete probability distribution? Because we calculate probabilities based upon individual values. What is the probability? X is equals to 0. What is the probability? X is equals to 1. What is the probability? X is equals to 5. These are some examples of binomial distribution. Now, if you remember, what is binomial distribution? X, the variable x, follows a binomial distribution with parameters n and p. N is the number of trials. And what is p? P is the probability of success. And also there is a symbol Q, which is probability of failure. And we know that P plus Q adds up to 1. Yes, there was a formula for calculation of probabilities. Probability X is equals to R, where R is the value for which probability is calculated. NCR, P raised to power of R, Q raised to power of N minus R. For example, if I'm talking about 7 days in a week and the probability that it rains is 0.3, probability it does not rain is 0.7. Now we can write the distribution for X. X follows a binomial distribution with number of trials 7. We are talking about 7 days, and the probability of success is the probability of raining, that is 0.3. And then we can use this formula to calculate probabilities. For example, if I'm interested in calculating the probability for 3 rainy days out of 7, that is probability X is equals to 3. So therefore this is 7C3. This is probability of success raised to power of 3, probability of failure raised to power of 4, and then using a calculator we will get the answer. Now this video is not about binomial, it's about Poisson distribution. So if I talk about Poisson distribution, what exactly are we talking about? Let me give you some examples out of which I'll be deriving the idea of Poisson distribution. If I talk about a telephone operator sitting in an office and receiving calls, if I'm talking about this scenario, we know that a telephone operator, for example, receives 6 calls in a 30-minute period. Now, such a scenario will be classified as Poisson distribution. Why is this so? Because there is an average number of calls within a certain time period. Let me give you another example. Let's talk about a piece of cloth, and there are flaws in that piece of cloth. So if I am talking about 1 meter length of cloth and there are 3 flaws in that 1 meter length of cloth, this 3 is the average number of flaws, and these average number of flaws occur in a certain length interval. Let's look at another example. If I talk about a radioactive substance and it's emitting particles, and these particles are coming out at a constant rate of 100 particles per day. Now, this is also an example of Poisson distribution, because this 100 particles, that is again the average number of particle within a certain time period, and that time period in this case is a day. So now we are in a position to define Poisson distribution. First of all, let me use the term average and its equivalent word, that is mean. Let me use the symbol lambda. This is for mean number of occurrences. So let me write occurrences over here in a specified time or space interval. Now, first of all, let me focus on the time interval. It could be per second, it could be per minute, it could be per hour, it could be per day, it could be per year. And if I talk about space interval, it could be in terms of length, like we just talk about a meter length of cloth. It could be about the number of particles in a particular area. For example, the number of seeds in 10 meter square area of a field. It could be about volume. For example, the number of microorganisms or the number of bacteria in 1000 centimeter cube of a particular solution. So all this will fall into the category of space interval, whether we are talking about length or area or volume. And the examples of time interval are all listed over here. So now let's define Poisson distribution. The variable x follows a Poisson distribution with lambda. What is lambda? That is just described above. That is the mean number of occurrences in a specified time or space interval. And the formula that we will use is probability x is equals to x, that equals to the exponential function raised to power of negative lambda, lambda raised to power of x divided by x factorial, where x takes the value 0, 1, 2, 3, 4. It goes all the way till infinity. So now this is the formula that we will use. Yes, Poisson distribution is a discrete probability distribution because we will be calculating probability based upon individual values such as 0, 1, 2, 3, 4 all the way till infinity. What is the property of Poisson distribution? For Poisson distribution, x follows a Poisson distribution with lambda. The word that we use for mean is also expectation or expected value. The expectation is lambda, and the variance of this variable which follows a Poisson distribution is also lambda. Therefore, it's a hard and fast rule that expectation of x is lambda, so is the variance of x. This is a property of Poisson variable, and this knowledge is also used in the topic of linear combination. Now, there are certain conditions that applies to Poisson variable, and in particular, it applies to the mean number of occurrences within a specified time or space interval. The first condition is that the mean number of occurrences occurs singly. The mean number of occurrences occur at random. The mean number of occurrences occurs at a constant rate. And last but not the least, the mean number of occurrences are independent of one another. Now let me explain all these conditions. So these things that I've written in orange color, that is the condition for a variable to be following Poisson distribution. Now let me explain each condition in the context of a situation. The best example that I can use is that of the telephone operator. If I use the telephone operator example, the data I had given in the beginning was that the telephone operator receives 6 calls per 30-minute period. Now let's look at each condition one by one. The first condition is about the mean number of occurrences occurring singly. The second condition is the mean number of occurrences occurring at random. The third condition is the mean number of occurrences occur at a constant rate, and the fourth is about the number of occurrences being independent of one another. Now in this context, if I talk about occurring singly, what does it mean? That means the calls will come one at a time. That is what it means by singly. What about the second condition? That is occurring at random. Yes, there are 6 calls that are coming within a 30-minute period, and this they have found from their experience, their past records. It does not necessarily mean that every 5 minutes the telephone operator will be receiving a call. It could be true, it could be false. The main thing is that within that 30-minute period, yes, the telephone operator will be receiving 6 calls. It could be that during the first 20 minutes, there are no calls. But in the last 10 minutes, there are 6 calls. Still, the average is the same, that is 6 calls in 30 minutes. Now, what is the third condition? The third condition is the mean is occurring at a constant rate. That means if I change the time period, if I change the interval of length or area or volume, the mean will change proportionally. So let's take the example of telephone operator. This is the number of calls and this is the time period, which in this case is in minutes. We know that there are 6 calls received in a 30-minute period. That means if I change 30 to 60, basically I have multiplied by 2. So therefore 6 will change proportionally and this will become 12. Similarly, if I take 30 minutes and if I divide by 10, so 30 will become 3 minutes and 6 divided by 10 will become 0.6. That is the average number of calls in a 3-minute period. Now let's focus on the last condition. The last condition is about independence. That means the mean number of occurrences are independent of one another. What does it mean in this context? That means the telephone operator receives the first call and then the telephone operator receives the second call. These two calls have nothing to do with one another. They are not influenced by one another. They are independent of one another. So now what have we learned in this video? We have learned that Poisson distribution is a discrete probability distribution. X follows a Poisson distribution with the mean number of occurrences denoted by the symbol lambda. The formula that we will use is this: probability x is equals to x, e raised to power of negative lambda, lambda raised to power of x divided by x factorial, where x takes the values 0, 1, 2 all the way till infinity. And then there are 4 conditions that are necessary for a variable to follow Poisson distribution. The mean number of occurrences will be occurring singly, they will be occurring at random, they will be occurring at a constant rate, and they will be independent of one another. In the upcoming videos, we'll be solving questions based upon the formula for Poisson distribution.